这不是直播画面吗？这是直播画面。是呀，就这意思，就这个屏幕也共享到了 YouTube， 同时这个互动也在共享。对，对。
看一下啊，不对呀，我这边屏幕现在也在共享了，但是它的没停，它怎么能显示我的共享呢？
你为什么要共享屏幕？
就是别人在讲的时候要共享。
讲的时候不应该在这上面
线上人讲，
线上人讲，
肯定要吗？然后他共享的时候，我这边应该也要能看到才对。
别人共享，他这个在电脑只要参加进去就知道了。
但现在这没有啊，现在没有。
你在共享？
对，我在共享，然后这边没显示我在共享，这个是我的号。我应该把这个关了，是不是？把我的共享关掉
啊？你在共享屏幕？
哦，这是我的共享。
哦，那正常人。
那我把这儿的共享要关掉吗？还是我把这个拖过去就可以了？
拖过去就可以。你先最小化吧。
这样，
最小化就可以。
这样。
对，最小化。
这样，这像是线上的共享。
啊，
对吧？
它只是共享那个屏。
共享，我现在是共享是我这个屏。对，它只共享那个屏。这样会上的人应该就能看到了吧？
对。你先
我先退了，
先结束共享。
我先结束共享。
不止结束共享，你要把它移过来。
OK。
现在的别共享，
要管。
其实你不用管，等一下那个打开 PPT 的时候会
就盖掉这个。
就是盖掉。
聊进。
一播放就会盖掉。
对，就盖掉了。
这样就可以。
然后这个聊进的。4啊。
下个
这条量我来复制，给它改一下。
不用管，来不及。你不要搞，不用管它，其他
它只有一页，小块的。只有一页有问题，只有一页给它。
不用管它，
这样。
一页没事，它一下就跳过去了。
啊。对。那这样，现在关掉。
不是第一个是我的。
啊。这样是对的啊。你有 PPT 吗？
对，好过来了。对。
为什么你打开就可以了？
对。咱们有没有简单的？行，以这个为这个还行。啊，对的，一定要讲，经常拿话讲。上啊，你不行，你刚才怎么往上下来。
Good afternoon, esteemed researchers and industry leaders, and distinguished guests from all the world. Welcome to the Grand Challenge at IEEE AICAS 2005. This year, the Grand Challenge features 3 technical tracks. First, let me introduce Professor Mo to give a brief introduction about this Grand Challenge. Let's welcome.
Thank you, everyone. I will give the short introduction of our Grand Challenge. I'm Wei Mo from CDN University, and I'm also the Grand Challenge Committee co-chair. And this time, Prof. Boli and Yuan Du are also the co-chair come to here on site. This is the organization committee from academy and the industry. Okay, the list. And this Grand Challenge has already lasted for 3 years. In first year, 2023, it was held in Hangzhou. The topic is software and hardware for optimization for commercial applications. And last year, we held it in Agami, and the topic is large language model acceleration. And in this year, our competition is began from December 2024, and it can last several stages from promotion stage, preliminary round, final round, and he's come to the final presentation stage. And in the Grand Challenge this year, we have already post the three tracks. The first is the large language model software and hardware system optimization, which is in charge by me. And the second track is large language model hardware system design, and which is in charge by Prof. Zhe Zhi from Shanghai Jiao Tong University. And the third track is large language model based analog circuit design competition, and which is led by Prof. Li from Xinjiang University. For track one, we working on the software and hardware optimization on large language model to optimize the model with less resource and high throughput on ARM CPU. And for the track two, we implement the LLM on FPG to increase the throughput and reduce the hardware resource. And for track three, we apply the large language model to circuit design to auto in this track, we set some specifics for analog design, for especially in op-amp. And our competition only running on the Tianchi platform. In the middle, after the preliminary round, and we also had a large workshop in Hangzhou to discuss the related technologies and invited the experts from industry to share their experience. In final, top three teams in each track are selected and stand out due to their excellent works. And congratulations to the winning teams. Most of them have come to the conference on site, and several teams are online due to the visa issue. So now in the following, the teams will share their works and share their text used in the competition. After the presentation, we will provide the award ceremony. Thank you.
Thank you, Professor Moss, for the introduction. Next, we will stage the academia and industry from keynote from ARM Corporation. Let's welcome the ARM expert to give a presentation. Hello.
Can you guys hear me? There's no again.
No, we cannot see your screen.
But you can hear me?
Yeah, we can hear you.
Of course, we can hear from you.
Okay, so I'm going to change the pattern a little bit. And instead of showing you the slides and maybe boring you, I'll just show you a few web pages that we have. And that should give you an idea of what we are doing on Gen AI in ARM, right? To make the Gen AI experience possible on CPU. Okay. So let's see. Maybe what I should do. So you can see me. Okay, give me. So what is this page? This page is showing LLM chatbot on the servers. And I will actually show you in operation. So this is running a Llama 8 billion parameter model, and it is running on pure CPU. This is not running, there's no GPU or anything of that sort here. So if I say, okay, this, I hope it goes.
但是没共享桌面。
共享了，这是他的，
对，但是你没显示这个桌面。
这边没显示啊。我这边能看到，但他看不到。
Llama CPP doesn't seem to know about this conference, but if I say, okay, what do you see right there? What is your, there's
我这边还不能共享，他这边为什么？共享一下吧。
This is running Llama 8B model, and it's
Okay, problem, but
you can see the performance.
oh, hi, Bet. Please wait for a little minute. 7 minutes. We are working on the sharing. Sorry.
Sorry, you can't see the share.
Oh no, we cannot. We are working on it. Sorry.
Ah.
Okay.
I'll just wait.
我这共享一下。
不是，这不是。
他刚把共享停了。他刚把共享停了。
Oh, please open your sharing.
What should I open? Sorry.
Can you share your screen?
Yeah. You coming?
Okay.
Share your video, but we cannot see your.
Okay, we can see your screen.
Okay, right.
Okay.
Okay, cool. Okay, sorry. I'll just go through this whole thing again. So today I'm going to show you 4 pages. I'm not going to show you with many slides. I thought it's not the slides, but then you can actually try this yourself later. So instead of me telling you that it runs fast or on CPUs, you can do LLMs on CPUs. You can see for yourself. So here we have Llama 8 billion model running on ARM CPU in the cloud. So this is Universe on CPU. There are 72 of them or 64 of them, if I'm recalling correctly. And let's see how fast it is. So I just asked about Llama, but let me ask about Quen one, right? Let's see what it says. What about Quen one? Right. So it says about that, oh, it is similar to that, and you can see that it generated roughly 57 tokens per second. And your human reading speed is something like 5 tokens per second. So here you could generate, this is all CPU, there's no GPU, and this is plain vanilla CPU. There's no fancy accelerator of any kind. So the reason for this is we have both hardware and software. Hardware is we have some special machine learning instructions. So if I ask for features common have or ML in hardware instruction, etc. See what it says. Okay, so obviously this. Let's ignore this. This is the wrong answer, but at least we have instructions which can make things like matrix multiplications go faster. And we have data type support for dfloat 16 and so on, right? Now, all that is great, but if you can't use it, there's no point. Now, for that, what we did was we did this glidey library. And the goal of this gliding library is it just goes fast without you noticing. So if you use PyTorch or anything of that sort, it'll just be faster, or even a mobile phone. Now, how do we do that? Is the marketing events, and let me show you what happens. Is if you take something like BERT or Llama, if you integrate Glide, basically our ARM kernels, then it improves the performance by a lot, like BERT stuff 2.2 times for BERT large. And Llama, we already saw how fast it goes, and this continues, right? But Thane serves as an example by Alibaba on ETN. All of this use the kernels that we have developed. Now, what are these kernels and how do they make it go fast? So the kernels are here. It's a GitLab project. It's called Glide AI today. And what it has is what's called a microkernel. Now, what is a microkernel? A microkernel is just a piece of assembly in most places which makes something go fast. Okay, so if I open, for example, let's say matmul microkernel, there are so many variants of matmul microkernel. And if I pick something that clamps and it is FP32 input, FP32 output, and so on, what does it have? So we have the kernel with SME, which is a hardware architecture feature, the kernel with Neon, which is a hardware architecture feature, and so on. And if I open one of them, let's say I open this, you will see that it has lots of okay, maybe we have to go to the implementation. Let's go to the implementation. That's this one. So you have these assembly code, and these are just codes from ARM that makes a particular function go fast using the hardware feature. So in this case, it is using the Neon feature, but it might be using some other feature. And how this gets integrated is either we directly work with a framework, like for example, in the case of PyTorch, we have integrated directly under A10. So any customer who's doing image detection and object detection, any of that, will use PyTorch, which will automatically use Glide AI, and then whatever underlying hardware features we have, it benefits from it. Right? So you don't have to do anything as a user, but if you have a special framework, special use case, something you want to go very fast, then you're free to kind of go into the Glide AI part and use these kernels, use these microkernels. Okay. And in the mobile space, it's being used by many different. So there's one for, I think, in executors for PyTorch, there's one in TF Lite, there's one for Android phones, and so on. I think even a China, Alibaba's some particular framework, they also have these kernels integrated. The main thing is it has no dependency on external library because all that it's just an assembly file. It doesn't do anything like memory management, dynamic, nothing, no threads, nothing. It's simple microkernels that uses different microarchitectural features. So, and once you use this, it's kind of maintained by ARM. So if you're going to use this, then there's an implicit guarantee that as and when we introduce new features or we make some new optimizations, you can be assured that these are the best possible performance that you can get. And you can see that it uses, this is what we call Neon. SME is similar to what AMX in Intel, x86 LAN. SME2 is the next generation of SME. So these are all hardware features, but you don't have to worry about the hardware features. You can just use a microkernel. And if you're using one of those standard frameworks, you don't even have to worry about microkernels. You can just use the standard framework and things go fast. Right? So this is what I wanted to show. What is the performance impact? Now, I showed you about the PyTorch thing where we used Live AI. What did it do before and after? So with 4-bit quantization, we could take the performance from something like 2.2, let the sum in be chat, 2.2 kilobits per second to 40 kilobits per second. Okay. Now, what it's saying is, by default, it was highly unoptimal. Maybe it was like a C code or something. And because we added this Live AI kernels, now it's 20x faster. Right? In this case, 18x, so on. So that's the performance you get. And that's what you saw. I mean, you didn't see PyTorch, but you saw Llama CPP, similar things, similar kernels. And that's what you saw when I typed questions here. And you can try it yourself. I mean, this is a public link. Just search for Llama CPU ARM demo. You can run it. And if you want to try it yourself, we have something called learning paths. It has complete instructions of how to do it yourself. So you can get the model, install the dependencies, and download the Llama CPP and everything else, and then just run it. Right? If you run it, basically using a quantization format, this is a line here. If you run it, then you can see it operation like this. Okay, so that's what I wanted to give. I didn't want to give you a big lecture of how great all of these things are. The key message to take is CPUs also can do things faster. CPUs are becoming better because we have special instructions, whether it's Intel AMX or ARM with SME and other things. And we're all doing enough things in software like AI that your performance is better than what most customers would want. So you don't need a massive GPU to do simple algorithms. Okay. Any questions so far? All right, I will.
Oh, okay, thank you for your enlightening talk. Maybe the audience, it seems there's no questions. Is there any questions?
I mean, if there's none, I'll give maybe 6 minutes of your time and maybe we can get the next presenter. Thank you very much for your time.
Thank you. Okay, maybe thank you for your support. Probably there are global pioneer in this area. Now next we can move to the track one. First of all, the first speaker. This topic is about fixed quantization of incomes.
Bonjour and good afternoon. We are the first prize winner for the track one. So the topic for us is a mixed quantization of a large language model inference. And at first I introduce the team members and the first one is Zhao De Wang, and the second is Jianhao Zhang. He's from Kunlun, and you guys may know him as Da Xian. And the third one is me. And okay, so what we are trying to do is just to deploy the 5 million parameter models on the ARM devices. So the pipeline for us is first, we are using the Hugging Face models, and we export it to Onyx and use Onyx Slims to do some model optimizations. And next, we will do some mixed quantizations. And finally, we use the MN framework to deploy the models and all the codes you can find through the link. And first, this year we do some model distillations. So the distillations can distill the capabilities of stronger models into the smaller ones. And the data sets involved in our distillations is some common available data sets and also some synthetic data sets. And as you can see from the table, after distillations, we have overall accuracy increase. So, and the models is also available through the following link. And then we use our Onyx Slims to optimize our Onyx models. And compared with last year, and we currently we have about 2 times the speed increase in half the memory usage. And now Onyx Slim is also becoming a community standards, and it's adopted by Hugging Face and Ultralytics and Paddle and Alibaba and also many other framework. Okay. And next, we just want to introduce the optimization techniques. And so first, we use is about weight quantizations, and next is disk embeddings, and also some half precision and memory reuse. And for weight quantizations, we for the Qianwen 5 million models, and the linear parameters is about 370 million, and the next is about embedding parameters. And if we don't use quantizations, it takes about 2 gigabytes, and if we use 4 bits, it's about 250 million bytes. And the next is about disk embeddings. So the embeddings, we have many embeddings that's and it's not called from the users. So we don't need to load it into the memories. So we just want to load when we really use it. So so this technique will save lots of memory space. And the half precisions and the memory usage, and we use flow 16 for activation and a KV cache. And the memory usage is just want to reuse the memory as much as possible. And next is about performance optimizations. And we first analyze the performance. Just like the large language models, it's a consecutive decoder blocks and a prefill and decode stage, and the 3 core operations like linear, matrix modifications, and memory parts. So for the prefill stage, you can see it's a compute bond, and the decode stage is a memory bond. So for the linear part, we use 4-bit weight quantization and 8-bit activation quantization to reduce the memory footprint. And we select SSMLA as the real computing instructions, and use loop tilings to improve the memory locality and make memory more efficient. And for the attention part, we use a float 16 for matrix mount, and we also use loop tilings to speed this. And then we use the fused multi-header attention kernels to reduce those memory reorderings, and we use high precision for softmax and RMS norms to retain the accuracies. So with our frameworks, and we have a baselines, and if we use the float, you can see the average score is about 45%. And if we use all 4-bit quantizations with group size as 128, the accuracy drops to about 42%. And if we use 4 bits per channel, quantization, it drops to about 3-4%. And if we use 8-bit group quantization and channel quantizations, the accuracy almost our baselines, but the performance will degrade. So so what we want to do is use as much as possible the low bit quantizations, and also want to retain our accuracies. So how can we do that? So this is about this year we introduced a new mixed quantization schemes. So that's available for almost every large language models. So here we have to decide which layers should be in lower precision and which layer should be in high precision. So a typical way of doing that is we want to search and search each operators, and we want to decide it and to get the result. But the search space can be really huge, and that's not efficient. So what we want to do is just to
recording in progress.
We want to, what the optimization goal for us is to maintain high accuracy and quantize the linear operators as extensively as possible. So this year we have a regressive genetic algorithm to be applied to these mixed quantizations. So what we are doing here is first, we want to create a matrix to decide which layer is more sensitive to quantization. So some layers may drop to very low accuracies when they are quantized. So how can we determine that? So what we are doing here is just we quantize each layer each time. So we get a baseline accuracy. This step we only quantize one layer, and we compare with the baseline from flow 16. Okay. After this time, and we can decide which layers on the low precisions have high accuracy, and we will keep it. And in step 2, we will have to search for the layer combination search, because for only one layer can retain accuracy, but if we combine many layers, the accuracy may drop to very low. So we have to search with these combinations, and this time we use a genetic algorithms, and we will normalize the accuracies from the first step, and with the low accuracies with high possibilities to be falling back to high accuracies. Okay. And this time we will search for the best candidate. And the third step is about operator combination search. So for each layer, we have seven linear operators. For the layers that was set back to high accuracy, set back to high accuracy quantizations, we will just trying to revoke it, and we want them to be in low precisions, but the previous result may be bad. So we just want to dig into the layers with all these 7 operators. We just want to revert those 7 operators layer by layer, operator by operator, to see if we can retain the high accuracy. So this time, after the third time search, we will get the final result. So with our mixed precisions, we have achieved about 20% less accuracies compared with the 4-bit channel per channel quantizations and with nearly no accuracy loss. And the performance is about 150 tokens per second. And that's all my presentations. Okay, thank you.
Thank you for the insightful presentation. Okay, let's welcome the next speaker.
Okay. Benjer. Good afternoon, ladies and gentlemen. Sorry. I'm Fan Ruchao, and our team, Michael, from the Southeast University, has taken the second prize in the track 1 of the AICAS Grand Challenge. And it's my great honor to present this report. And my topic is an accurate and efficient framework to deploy the Qianwen 2.5 module on ARM CPU. And first of all, I'd like to introduce the basic information of our laboratory. We come from the 601 Circuit and System Lab from the Department of Electronic and Science and Engineering in Southeast University of Nanjing. And we have some directions such as FPGA, EDA, the point cloud, and the quantum computing. And we have 5 members in this grand challenge, including the Zhao Wenyuan, the Cang Zhao, Ye Xiang, Gu Yuhang, and me. And we have 3 main advisors. They are the Professor Tang Yongming, the lecturer Sun Hao, and the Professor Li He. Okay, let's begin with our topic. This figure shows the overview of our framework. And our optimizing strategies can be divided into 3 parts, including the fine-tuning, the quantization, and the inference optimization. First, we use Llama Factory tools to fine-tune the original module in multi rounds, and then we get the full precision module in safe tensor format, and then we use Llama CPP to convert the safe tensor format into the GGUF, and then we conducted the 4-bit quantization to obtain the interval module, and finally we have conducted several in backend inference optimization methods. And first, let's start with fine-tuning. Fine-tuning is used to improve the module's accuracy on the 3 evaluating data sets, offsetting the precision loss caused by the 4-bit quantization. And as shown in the table 1, we have 3 evaluating data sets in the final round, including the ARC challenge, the HALSWAG, and the C-evalu. This competition doesn't allow the use of the evaluating data sets for fine-tuning. Therefore, we found 7 kinds of the relevant data sets, which are shown in the table 2. They are the Alpaca GPT, the Ultra Chat, the Venogrand, Swag, Story Close, Common Sense QA, and Simlu. Okay, and now we get the 7 data set for fine-tuning. Then we conducted the multi-round fine-tuning with these data sets. And this figure shows our fine-tuning tree. First, the root node of this tree is our original module, the Qianwen 2.5.5b. And first, we fine-tuned this module on all 7 data sets to obtain the module LoRaWAN. We can see the accuracy of the LoRaWAN. The improve of the LoRaWAN is very limited. And then we try to maintain the original module on two data sets, the Alpaca GPT and the Ultra Chat. This step aiming to improve the logic reasoning ability. And then we got the module layer 2. The accuracy of the layer 2 has demonstrated about 1% improvement. And then we use the remaining 5 data sets to obtain the LoRa 2.1. And this module shows the best accuracy, which demonstrates the 1.61% higher accuracy than the original module. And finally, we have tried the extra 2 rounds fine-tuning based on the module LoRa 2, but the accuracy is not as high as the LoRa 2.1. Okay, and this slide shows the loss function comparison. We compare the 1-round fine-tuned module, the LoRaWAN, with the 2-round fine-tuned module, the LoRa 2.1. And on the right is their loss function curve, and we can see that the loss curve of LoRaWAN exhibits significant fluctuations and failed to converge. And the LoRa 2.1 is smoother and converges more rapidly. The main loss of this module is about 0.2, and this shows the superiority of the multi-round fine-tuning. And our second part is the quantization. The quantization can lead to a loss of precision, but it can significantly optimize the computing efficiency, including the prefill throughput, the decoder throughput, and the memory usage. And the Q40 and Q4KM are both the quantization methods of the Llama CPP. And we can see that the accuracy of Q4KM is slightly higher than the Q40, but the throughput and the memory usage of the Q40 is much higher than the Q4KM. So the Q40 shows the balance between the accuracy and efficiency. And our third part is inference optimization. And first, we'd like to select an inference backend. The original demo is based on the PyTorch, but we select the Llama CPP, which is based on the C++ and is more hardware friendly. We conducted three optimizing strategies of the backend inference optimization. The first is the matrix tiling. The matrix tiling strategy can significantly reduce the probability of cache miss and improve the inference efficiency. And the second one is operator optimization. It uses the instruction sets such as the NEON, the SVE2 to accelerate the matrix operations. And thirdly, we have made some configurations to the compiler, which can improve the running speed of the program. And as a result, the three evaluating data sets has different evaluating weights, the 0.1, 0.8, and 0.1 respectively. And you can see in the table 4, in the final line, our fine-tuned and quantized module achieves the 0.68% higher accuracy than the original model. And the second is module efficiency. Our test environment is E10 710 CPU in 32 GB memory. And this table shows the inference efficiency of our framework. And we can see that our optimized module, which is based on the Llama CVP backend, has been greatly enhanced. And that's my references. And thanks for your listening. That's all my sharing. And thanks to my teammates. Thanks to the AICAS committee. Okay, thank you.
Thank you for this example one. Now we can have the next speaker giving a talk discussing about foundation layer 3.
Hello everyone, I'm Neng Hao Chen, and I'm the third prize winner of the track 1 in this competition. Since my English very poor, Ina Zhao will help me in this speech.
I'm Ina Zhao. The title of my presentation is 13% size, 100% accuracy, a quantization-aware training framework compatible with Llama CVP. My presentation will include the following sections. Number 1, introduction to current quantization or methods. What is quantization-aware training? Introduction to the Q40 format in Llama CVP. How we apply the quantization-aware training to our model. And next one, experimental results. The last one, additional attempts and expand discussions. Why are we focusing on quantization? Why are we focusing on quantization technology this year? The first reason is through last year's competition, I believe the optimization potential in low-level implementation has become limited. The top performing method in last year's competition approached the theoretical limit of hardware computational power. The second reason is quantization technology optimization is less dependent on specific hardware platforms, which facilitates the migration of our optimization methods to other platforms and offers great flexibility. Principle and methods of quantization. Numerical values in computers can be represented in various formats, such as floating point representations like IP32 and IP16, and integer representations like int 32, int 60, and int 8. Quantization typically reduce the FP32 FP60 values to low bit representations like int 8 or even int 4. Model quantization is a technique that map floating point values to low bit describable values. It can effectively reduce model parameter size, memory consumption, and inference latency, but often results in significant accuracy loss. Principles and methods of quantization. Model quantization methods can be categorized into the following three types: quant-aware training, QAT, post-training quantizations, dynamic, PTQ dynamic, post-training quantization static. Simply put, the key to QAT is to use fake quantization nodes to simulate the loss in the quantization process. The Q40 data type in Llama CPP. Q40 is a 4-bit symmetric quantization format designed to convert the original model's floating point parameters into 4-bit integers, thereby reduce memory footprint and computational workload. In Q40, each quantized block shares a scaling factor to map the integers back to floating point values. We inserted the following fake pointer nodes in the green section of the diagram. We performed QAT quantization on the model, used a place cleaned dataset, trained for a total of 4 rounds, then quantized the width to int 4, resulting in the final model. The detailed parameters are as follows. As you can see, our method does not lose any accuracy compared to the baseline. During the competition, in addition to the aforementioned work, we also made some other attempts. However, due to factors such as limited resources, time constraints, and feasibility, these methods were not ultimately applied to the final results. Nevertheless, these approaches could be explored further in the future. Parallel decoding of hiding layer features based on token. Speculative simply. Static allocations in the computation graph backend. Why is quantization-aware training rarely applied in large language models? If standard quantization-aware training methods are directly applied to large language models, the GPU memory consumption is almost as high as during model pre-training. The excessive resource demand makes it extremely challenging for ordinary users to perform quantization-aware training on large models. Additionally, QAT requires a training dataset. If the dataset is poorly chosen, it could potentially damage the original model. Fortunately, I have already found corresponding solutions to the two challenges mentioned above. Regarding the first issue, my upcoming methods enable quantization-aware training for a 332B model use only 24 GB of GPU memory. For the second issue, we can achieve dataset-free QAT through data-free distillation, ensuring the quantization model maintains the same distribution as the original model. I will soon release a software package to implement the aforementioned features. The quantized results will be directly compatible with the crossing platform in inference framework, Llama CPP, an achievement that has never been released before. If you have any questions, please contact me. Thanks.
Thank you for that presentation. Now we will transition to track 2. Track 2 focus on deploying large language model to LPG. Now we can let's welcome the first speaker.
Hello? Can you hear me?
Yeah, we can hear, but the voice is quite small.
Can you hear me? You cannot hear me.
Please wait for a moment.
Please share the options of sharing of the screen is always cannot share to you. Please share this. Arrêtez le partage. Just under this, the red things.
Okay, this one?
No. The purple one. Okay.
Can you hear my voice?
I don't think it's sharing.
你在共享屏幕吗？ 能听到。
Yes, we can hear from you, but I'm not sure you can hear from us. Okay.
Are you sharing screen?
Are you sharing your screen? Yeah, we cannot see the pom-pom.
线上，下一个也线上。他在换一个设备。
Well, can you hear my voice again? Yeah, we can hear you.
You can share your screen.
You can turn off the video to speed up. Okay, 靖宇国 can you hear us?
对，这就行。让他没有共享屏幕。
你那边可以共享屏幕吗？
或许你在共享这个屏幕1和2，来切换一下共享屏幕。
哦，可以。
可以。
对，但是听不到视频啊。
可以了，你可以开始讲了。可以。
可以听得到声音了是吧？
对，
开始吧。
你可以开始了。
Okay, sorry. This is an accident. I'm honored to present our work as decoding full stack optimization for decoding our mesh process. I am extremely bold and from so here is the simple background for the next LLM acceleration. As shown in the figure, most LLMs, for example, ChatGPT, they're deployed on the cloud so they can offer better stability to more complex. However, for this solution, several issues will exist. For example, they will rely on internet connection, and there will be privacy and preserving problems, and there will be latency problems. So we have the right side, the edge-based solution. So the edge-based deployment is helpful, but there are several challenges. Resource capability and power, and etc. So we are here to present a solution that can fill the gap. Before presenting our work, we need to talk about the challenges of deploying AI. And the first one is the bandwidth utilization problem. So as shown in the figure, most previous works suffer from a bandwidth underutilization problem, which means they can only utilize a part of the available bandwidth. And the bandwidth is usually limited on edge computing devices, which is typically around 10 gigabytes per second. And this underutilization will degrade the components or throughput. So we have a simple calculation format equation on the right side, which is the token per second actually is calculated by the bandwidth divided by the bit size. And the simple that accurate estimation is too low. For the channel model, it is 0.5 billion. And if we consider it to be 8-bit quantized, and on T860 FPGA, we have measured around 10 gigabytes per second. So for TDS, we can calculate it by this division, which is 20 tokens per second. And this is the theoretical proof, so no solution can go over it. And so with the underutilization, the throughput will degrade to 13 tokens per second. So this is a big challenge. And this underutilization comes from several sources, like production overhead or time embargo. And the second challenge is complicated number operators. In the large language model, there are several complex non-linear operators like CU and EXP and so on. So this computation are crucial, and inaccurate computation will cause
great accuracy degradation. For example, the complexity will just explode. And for our device, the TB216, it only contains around 1,000 ESPs. So it is not possible to support all the including things, which will consume thousands of ESPs. I'm pretty sure I worked at AICAS and AICAS. They have also explored some solutions. For example, they created methods for debugging. And we have several defects. For example, wiki methods, they require to fine-tune the original architecture model. And for the polynomial methods, it can handle models like BERT. But for large language models, it contains outliers, so it cannot handle this problem. So we are here to present our solution. Its name is edge decoding. As the name, it is a decoding solution on the edge. And so on the left side, we have the overall figure for our architecture. And on the right, we have some key metrics for this acceleration solution. So it's an architecture designed to fully utilize the hardware bandwidth to avoid the underutilization problem. And it also provides a systematic methodology for the nonlinear and including efficiency. And we almost consume all the resources on the board to achieve as high throughput as possible. And we achieve the critical speed of 288 tokens per second and decode speed of 35 tokens per second. And we also demonstrate our model accuracy to prove that our completion or approximation didn't cause any accuracy degradation. So here are our methods. The first one is a very aggressive vision of the whole decoder block. So I believe everyone has heard of operator fusion, but what we are doing here is really aggressive, which means we use the whole block, or we use the whole multi-headed vision. Actually, this scheduling, we utilize the feature of every state, which means there are several heads, and each head is computed independently, so we can implement each operator here immediately, like the computation algorithm. The sort max, we can implement them with unique models, and as they can be computed in a pipeline manner, so we can avoid any bandwidth underutilization. And to avoid the tensor lifetime completion, we use the tuple buffer or the force, the Q, P, and we use tuple buffers. And we have deterministic underutilization, which is in our simulation is less than 1%. So this is efficient. And for the MLP block, we have another technique which is fine-grained operator fusion. So there for llama-like models and genuinely llama-like, and it has two branches, the up branch and the big branch. And we do a fusion in the relationship of the alignment of our alignment. And so we can just calculate the part of it and immediately do the CPU as any device. So we can quantize it in place. And this technique can save 2.02 megabytes on chip storage. So this optimization is critical. And we also achieved an underutilization less than 1%. So efficient. We have a fully static and predictable computation behavior. So we can just consolidate the big axis behaviors into long bursts. And we can achieve as high, we have achieved very high bandwidth utilization. So this is our first method. And the second method to solve the nonlinear problems is the lookup table method. So lookup table is not new, but we have incorporated our techniques in our previous work, HT type. So we can use the POP approximation technique to index the DSP unit table. So when computing the index, we don't need the DSP. So it's more resource efficient. And to handle the outlier problem, we just used a straightforward solution. We provide several segments. And with each segment, it has the exponentially growing dynamic range, so it can handle the outlier. And as a result, all nonlinears are implemented on the chip. And we only cost less than 20% resource cost for these nonlinears. And we have some other minor techniques like the embedded table cloning. So table is a very small, but zero. But the embedded table is just too large. So we only retained 25% of the vocabularies. And with this technique, we improved our compression rate from 44% to 67%. And finally, we demonstrate our experience. And this figure is the device we use of edge decoding. And this is a very sufficient implementation. We utilize over 70% of LUT and 68% of DRAM. And so almost consume all the resources. And we simply cover these modules in this layout. So you can see each one. And finally, we have a real-time demo. It can achieve 35.2 tokens per second decoding speed and power efficiency of 5.586 per joule. And the power is measured on another. So this demonstration is real time and really runs on the FPGA, and it's real time. And that's all. Thank you for listening.
Thank you for the presentation. Congratulations to you that first place of this track. Now let's welcome the next speaker. Even the second place of the track of this track.
Can you hear me?
Yes, we can.
Yeah, I'll share my screen. Okay.
Okay, you can start.
Hello, I'm Changhao here from PPUZZ in university. Today I will introduce OPI, co-optimized FPGA framework for efficient edge inference of large language models. And here's my team members: Xinwei Zhou, Yi Ren, Xipeng Dong, Justin Zhang, and our advisor is Huang Yushen from School of Integrated Circuits University. So, a brief introduction. In recent years, transformer-based large language models such as ChatGPT, DeepSeek, Llama, and Qianwen have demonstrated remarkable success. These advancements have created new opportunities for deploying LLMs in edge computing environments such as intelligent assistants and the Internet of Things. And edge FPGAs are well suited for edge deployment for large language models due to their hardware programmability and energy. However, edge FPGAs present certain limitations, including constrained storage and computational resources. So since Chengyu has delivered a detailed analysis in this part of this, dive right into our topic. To address the above challenges, we propose a hardware co-optimization framework for efficient large language model inference on edge FPGA in the top. And our framework consists of 4 key techniques, including model optimization, operator acceleration on FPGA and CPU, and operator scheduling. So our first objective is to compress the model and fit model into limited tokenary, and we fulfill this goal with weight activation quantization. So we quantize the weights to 4-bit, which significantly reduces the memory footprint. We also quantize the activation of linear layers to 8-bit. In this way, we can adopt integer-only matrix multiplication, which is more hardware friendly over the floating point. As for quantification algorithm, we adopt PWQ, which protects scaling weight through channel-wide equivalent scaling and thus maintain model accuracy. And we use the open source code from LLMC to implement model quantification. And our second objective is to accelerate model inference with limited computational resources. We find that the primary bottleneck of large language models is matrix multiplication, which contributes to more than 90% of the overall execution time for the original models. So we propose to accelerate matrix multiplication with customized FPGA kernels. And the kernel consists of 3 main models. First, 3 on-chip buffers are employed to data reuse. And second, a map array includes multiply accumulate operations based on inner products. And third, a controller manages the block-wise data transfer between buffers and system host memory. And given the different arithmetic intensity between the prefilling stage and decoding stages, so we deploy separate kernels for GENN and GENV operations. We developed a parameterized RTL kernel template to instantiate these matrix multiplication kernels. And to further improve performance, we also employ techniques such as double buffering and frequency optimization, which will now be detailed. And finally, we introduced the hardware and software interface. We use the immediate buffers created by citing runtime library data between CPU and FPGA. And to simplify the on-chip data flow, we use CPU to reshape the input activation tensors to the customized data layout as shown in the figure here. This reshaping operation is fused with activation quantization and dequantization to improve efficiency. And after offloading the matrix multiplication to FPGA, the remaining operations executed on CPU become the new system bottlenecks. Therefore, we developed CPU acceleration techniques further improving efficiency. We start with replacing the self-attention operation at the fulfillment stage into backup. So the basic idea is you take a block of Q and K to calculate a subblock of attention score. And once you have this, you multiply it with a subblock of matrix B and use it to update the final results forward. So in this way, we can replace the original G and V operations with block G and N operations, which significantly provides higher data reuse and arithmetic intensity. And additionally, we use OpenBlast to compute G and N on CPU because it has better performance over a simple nested loop implementation. And we also propose to exploit the inherent sparsity in self-attention. We adopt the insight from streaming LLM, which empirically discovers that the initial tokens and the most recent tokens demand higher attention. So we can compute the attention score for these important tokens and directly set the attention scores to zeros or other trivial ones. So this idea can be simply integrated with special just mentioned, where in the attention score matrix, we only compute the leftmost blocks and the blocks near the diagonal, as shown in the figure. Compared with the dense attention, we can skip a large amount. And next, we accelerate exponential functions with approximation. The exponential function plays a crucial role in linear operators of large language models such as softmax and speech groups. However, the implementation from the official CMAP library exhibits suboptimal computation efficiency. To address this limitation, we approximate the exponential function with the first order Taylor expansion. It only requires one multiplication and one addition, but its maximum error rate is only 3%, which has little impact in the context of LLM input. And to further enhance performance, we carefully orchestrate the execution of CPU and FPGA. We use asynchronous execution on FPGA kernels, so the CPU doesn't have to wait for the completion of FPGA operations. And we carefully analyze the operator graph and try to overlap the execution of CPU and FPGA. So in this way, we maximize the hardware capacity. And finally, the experiment results. We evaluate the effectiveness of copy on Channel 2.5 model with 0.5 billion parameters. The experiment is carried on AMD Nvidia TV to 65, and we achieved a compression ratio of nearly 75%, owing to 4-bit rate quantity. In terms of model accuracy, our framework attains 48% on final runtime. AWQ largely maintains the model accuracy and blocks sparse attention and exponential function approximation introduce negligible accuracy benefit. Regarding inference speed, our framework achieves nearly 188 tokens per second during computing and nearly 10 tokens per second during decoding. And we achieve significant speed up for linear layers, self-attention layers, and switch-rule operations. And eventually, the operations on CPU and FPGA consume a comparable amount of time. So the acceleration on both sides make meaningful contributions to overall speed up. We also show the implementation details of FPGA kernels. Thanks to weight activation quantization, we can use integer-only matrix quantization, which can be efficiently implemented on the FPGA. Thank you for listening. If you have further questions, please feel free to contact us.
Thank you for the presentation and congratulations. Then we have the speaker from the the team that won the third place of the trial. I can hear from.
啊，这是 PDF，对，把它拖到那边去，行啊，拖到那边，然后看不见，对，把它拖一下。啊，可以的。我这边能隐藏吗？我右边隐藏了，这样。这样讲的，可以吧？可以吗？可以吗？嗯。
Good afternoon, everyone. Today I will talk about ALM, an FPGA-based LLM accelerator for end-to-end Quen 2.5 inference. And we are a team from Fudan University. Our team members include Ma Yujie, Li Linqi, Deng Yuman, Huang Zhirui, and directed by Professor Chen Shixiao and Professor Su Haozhe. Firstly, large language models have demonstrated exceptional performance across diverse natural language processing tasks. But the exponential growth in computational demand and along with diverse model architectural and along with diverse model architectural optimizations create urgent demand for edge device deployment, driving the need for innovative high-throughput hardware architectures. And for the challenge, first challenge is the prefilling process typically requires on-chip memory resources that far exceed available RAM capacity in the FPGA chip, while the per token decoding phase leaves most memory resources underutilized. And furthermore, full precision computation incurs prohibitive area overhead, whereas low bitwise degrades in inference accuracy. Additionally, traditional implementations offload nonlinear operations to the CPU, incurring performance latency from both data transfer overhead and the low parallelism execution latency. But the execution of nonlinear operations on the FPGA scheme faces the area and accuracy trade-off. Here come the features of our architecture. Firstly, we design an end-to-end LLM inference architecture. Secondly, memory-friendly data flow of prefilling and decoding phases. Thirdly, we design a dynamic precision computing unit, including precision configurable DSP systolic array for W4A8 or W8A8 linear, for W4A8, W4A8 linear and W8A8 attention computation. For the prefilling data flow, the primary challenge is mainly caused by the limited capacity of the RAM, which cannot accommodate all tokens involved in the computation. So we designed a data flow that divides the tokens into several blocks and process the blocks each time. The computation flows a block-wide execution pattern where each token block completes all processing stage, from caption layer Q projection to the next layer KV projections, and before proceeding to the next block. The design requires explicit data synchronization only for the KV cache before the attention of the next layer, and there is no synchronization during the whole processing. This strategy significantly increases weight transferring to prevent loading weight from becoming to prevent weight loading becoming the bottleneck. The token block size must exceed a minimum threshold determined by the memory computation ratio. And for the decoding data flow, conventional single token decoding exhibits zero latency imbalance, while the computational delay is dominated by the KV cache asset overhead. Meanwhile, single token processing leaves memory and compute resources with poor utilization. Consequently, we implement a selective KV cache data flow strategy. The most recent tokens, more than one token, proceed full KV with computation, while the remaining KV cache is stored off chip and transferred as needed. And the ratio between full KV computation tokens and transferring from DDR tokens is from 1 to 7 to 226. In this similar way, this strategy achieved a 10% reduction in heavy cache transfer latency, while balancing memory computation latencies and enhancing on-chip resource utilization. And in the metric core, it can compute token matrix multiplied with weight matrix or K matrix, V matrix in W4A8 or W8A8 block-wisely. And in the matrix core, each DSP perform 2 MAC per cycle, and the systolic input and the piped output solves routine congestions, which avoid fan out of the input operators of activate and wait. And and for the evaluation of our hardware, we designed an W4A8 quantization while training. We adopt methods that full parameter fine tuning and a smooth quant PTQ for linear together. And we use data sets WNLI for validation and testing according to the requirement of the grand challenge. And as for the result, we achieved the better result at a W4A8 static QAT plus PTQ, which achieves 99% accuracy. However, for some bugs in our hardware, we haven't achieved the same accuracy on our hardware. And for the FPGA layout and utilization, our maximum utilization rate was reached under the routability at 300, and the on-chip RAMs are nearly entirely utilized. As for the performance and comparison with SOTA-Works, we achieved 307 GOPS throughput at 1300 clock frequency, and 280 token per second in prefiring, and 1.9 token per second in decoding of Quen 2.5. We start off half of 1 billion. And for the conclusion, we designed an FPGA-based accelerator with memory-friendly data flow scheduling scheme and a dynamic precision computing unit, and we achieved 307 GOPS at 300 clock frequency operation frequency. And for the meaning of our work, we achieve efficient solutions for memory unbalance in pre-filling and decoding, and we consider the trade-off between accuracy and the computation resource. This is the introduction of our work. Thanks for your attention.
Thank you for your presentation and congratulations. Now we will move to the track 3. Track 3 explores a large language model in automating analog and mixed signal circuit design. And let's welcome the first speaker, who ran the was also won the first prize, place in this track.
Hello. There something, can you hear me?
Yes.
Okay. I'm so sorry about that. I didn't have the camera driver, so I didn't open the camera. Okay. Hello everyone. It is my great privilege to present our work as the first place winner in Trial 3 of this competition. Our team from the National University of Defense Technology, China, we share our exploration of expanding the potential of large language models in circuit design through our methodology titled the Industrial General Exciting Effective Multi-Stage LLM-COT Reasoning Framework. And based on the competition problem statement, we distill the challenge into an industrial AI design task by synthesizing evaluation and the practical constraints. And this process demands extensive simulation iterations and relies heavily relying on human expert domain knowledge. As illustrated in the right figure, it described the full cascade two-stage operational amplifier circuit typology adopted in our competition and trial. Well, while the loads, you can see from the picture the sizing process to make sure the size of every device in this topology. And since this is our first foray into leveraging LLM for amplifier design, we have systematically reviewed existing methodology to incorporate their strengths. Specifically, and we can see the analog coder automates AMP design by our large language model driving architecture synthesis. And Atelier employs a multi-agent framework with RAG, enhance the large language model for library generation. And the last method employs the large language models with various optimization algorithms for efficient emphasizing. And this is the framework of our method. And you can see from the left of this figure, the plan agent to call audience into local task rotation based on the properties of lines. And the AMP sizing tasks are organized into three progressive optimization stages. And we can see from the first part of this figure. And each stage comprises level state initialization in 2, and the subsequent iterative optimization in 3. And concurrently, expert knowledge is injected into the large language model to enable cross-processing, cross-structure generalizations. And in our approach, we employ multi-agent collaboration large language model to achieve the goal. And as illustrated in this figure, the iterative optimization framework based on multi-agent collaboration with post-training large language model constitute the core component of our method. And the optimization process operates cyclically and from 3 steps. The first step, the simulation agent conducts an ng-space simulation using current state markers. And the second step is the optimization agent generates collaborative prompts for the large language model to drive optimization strategies. And the third step is the resizing agent implements parameter adjustment and update state flags, completing the iteration cycle. And this is our multi-agent framework. We can see the planning agent receives industrial performance specification strategically allocated optimization task through large language model feedback analysis and orchestrate agent invocation. And the initiation agent collaborates with large language models through a structured prompt containing PDKs and industrial performance requirements to generate parameter computation code, and followed by automated verification and execution, building robust initialization analysis. And the resizing agent adjusts the circuit parameters for optimization performance, and the simulation agent evokes the ng-space to execute simulations. and generate the optimization agent to just use the large language models to facilitate the to resizing. We can, the next is the multi-stage of our method. We propose a three-stage progressive resizing methodology leveraging the dynamic decision feedback capability of expert knowledge injection, large language model, COT reasoning. And stage one, the certain optimization with the ideal current using the ideal current source, the initialization agent and large language model code generate netlist based on the process parameter. ng-spec simulation extract key metrics with TT corner OD evaluations. Post training large language model feedback guides iterative optimization until the specifications are met. And stage two, the circuit optimization with the bias current. A biasing current replace the ideal current source. The agent large language model system inherits stage one result to generate bias incorporated netlist. Target current optimization requires only TT corner current simulation enable rapid conversions. And stage three, total circuit optimization optimizing. In this stage, the co-optimization framework ensure maximizing industrial FOM through corner aware performance turn. And this is the initiation cooperated with LLM in our framework. And during the initialization phase, our primary objective is to rapidly and accurately generate the initial netlist based on industrial grade specification and PDK constraints. And the framework process design specifications through structured prompt engineering to generate the executable initialization code. And the initiation agent subsequently validate and execute the code in sandbox environments to ensure that the initiation netlist is accurate. And this is the pipeline we invoice and fashion this expert knowledge injection pipeline. And this pipeline architecture used the emphasizing in Sky 130 technology as a case study. Expert optimization strategies are first formalized and subsequently driving iterative simulations. In addition to experiments conducted on the competition provide Sky 130 process, we further validate our approach across 4 additional open source PDKs and distinct amplifiers of topology. Conclusively demonstrating its generous fully across fabrication, process, and circuit architectures. And this is the validation experiment result of our work. And from the table 1, the Chen-Wen 2.5 coder 3B achieves the optimal efficient performance trade-off and was selected as the final configuration. The 0.5B planned is the model achieves an 83.7% reduction in inference time compared to the 7B counterpart, while maintaining comparable accuracy. And concurrent, our optimization through 3-stage refinement reduce simulation iterations by 94.1%, achieving a 93.9% reduction in total computational time. You can see from the right figure. This is the validation experiment of methodology, and we just say that we proposed the methodology to inject the expert knowledge to large language models so we can do the cross processing, cross structure and deciding. We can see the result from the table when we do the cross or process structure combination while maintaining 73% performance consistency, conclusively confirming its effectiveness in cross process and cross topology and resizing. And this is the competition result. Beyond the competition scoring metrics, we integrated industrial grade figures of merit to steer next generation towards practical design constraints. And we achieved the higher side in power consumption and the maximum voltage gain. And we choose this the FOM improvement to range from 5% to 71%. Thank you for your attention.
Okay, thank you for your presentation. Congratulations. Now, we have next picture who won the second place.
Hello, everyone. I'm Jin Yishen. From Team 306 EDA Go Go Go. Our team members include Ji Zhuang, Zihao Chen, and me, and we are supervised by Professor Fan Yang and Professor Xuan Zeng. This work was completed at Fudan University. And today I'm honored to present our work titled Automated OPAMP Parameter Design based on multiple large language model agents. Today I will walk you through our approach, key insights, and experimental results. Analog design is one of the hardest tasks to automate, especially when it comes to operational amplifiers or OPAMPs. Although LLMs like GPT and Qwen have shown promise in analog circuit topology generation, parameter design remains largely manual. This process involves precise calculations, domain expertise, and time-consuming simulations. Our motivation is to automate this challenging step, parameter tuning, using a coordinated system of LLM agents. We envision a design assistant that takes circuit specs and automatically proposes transistor sizes, runs simulations, and improves the design iteratively. This will save analog designers considerable effort and enable faster prototyping of complex designs. Our goal is to build such system using only general-purpose LLMs, without domain-specific fine-tuning, and demonstrate that LLMs, when guided correctly, can automate even sensitive analog design tasks. However, there are significant challenges. First, LLMs lack built-in understanding of analog principles, like the effect of increasing on gain. Second, they cannot inherently do accurate numerical calculations. For example, computing the WL ratios or Ohm's law requires external tools. Third, OPAMP design is all about trade-offs. Improving gain often reduces bandwidth or phase margin. These trade-offs are nonlinear and circuit-dependent. Therefore, a single pass answer from an LLM is insufficient. What's needed is a looped, rule-based flow done by LLM agents. We address this by structuring the process into iterative stages and giving each stage to a LLM agent. Our proposed solution is a multi-agent LLM framework. We split the parameter design task into 4 specialized roles: design agent, calculation agent, simulation agent, and revision agent. Each agent receives a prompt with structured input and specific instructions. The design agent begins by identifying key specs such as tail current or input transistor length. The calculation agent computes WL values. with external tools for precise computation. The simulation agent runs DC, AC, and transient analysis using ngSpice. Finally, the revision agent compares the performance against the target and applies rule-based corrections. This cycle repeats until all specs are met or the maximum iteration is reached. We maintain a centralized data structure that tracks the netlist and parameters. Agents communicate updates through this structure. This approach allows us to use off-the-shelf LLMs like Queen 2.57b without any fine-tuning. Instead, all the domain knowledge is encoded in the prompts and tools. We pre-specify the op-amp topology as a telescopic cascade amplifier. This structure is well known for high gain bandwidth, excellent phase margin, and low power consumption. It has a single amplification stage and does not need frequency compensation, which simplifies the design process. It also consumes less headroom due to its low voltage current mirror loads. The op-amp runs at 1.8 voltage and drives a 2 picofarad load capacitor under the Skywater 130 PDK. This choice ensures that the design problem is non-trivial but well-bounded. The design parameters include the width and length of all transistors, as well as the resistance value for the bias resistor. The telescopic structure provides a meaningful testbed for evaluating how well our agent framework can tune sensitive parameters. Let's go into more detail about the role of each agent. The design agent starts by setting core variables like input transistor length and tail current. It follows heuristic rules such as using short length for speed and long length for output resistance. The calculation agent then computes the WL ratios and the resistance value using pre-coded Python tools. These computations are invoked by the LLM dynamically. The simulation agent writes netlist and calls ngSpice for DC, AC, and transient simulations. It only simulates the TT corner to save time. The revision agent reviews the simulated matrix, gain, phase margin, GBW, and so on, and modifies the design parameters based on encoded adjustment rules. These agents operate in sequence and repeat for several rounds. The orchestration framework coordinates them and stops when all the specifications are met or when a maximum iteration limit is reached. This division of responsibility mimics a real human design team and leads to a structured optimization. Our agent prompts rely on a compact knowledge base with just 357 tokens, yet it encodes all the critical design knowledge. This includes the descriptions of transistor roles, such as inputs needs high transconductance and the loads needs high resistance. We also encode initial design rules, for example, the min and max values for W and L based on the PDK. We include adjustments rules too, such as increasing channel length to improve gain or reducing area to improve phase margin. This knowledge base is selectively injected into the prompts of the relevant agents. The design agent uses for initialization and the revision agent uses for performance tuning. This setup ensures the LLMs are making remain general purpose while still reasoning like analog experts. We tested our framework on a real-world design task and tracked every iteration. It took just 4 iterations to converge to a valid design. In iteration 1, the design agent sets input channel length to 0.15 micrometers and maximum area was set to 200 square micrometers. The simulation showed insufficient gain and PM. In iteration 2, input length was decreased and area was halved to reduce the parasitics. This continued into iteration 3, where more tightening occurred. By the fourth round, we hit all the specs. The total runtime was 128 seconds, which is 2.7 to 19 times faster than any other valid submissions. Most of the time was spent in calculation and revision agents, which makes sense given their heavy numerical workload and design rule application. This experiment shows that our agent system can iterate, reason, and optimize like a real designer quickly and consistently. On this page, we show the optimized OPAMP design and the optimized design parameters in this design. The two figures on the left of the page shows the AC performance curve and the transient performance curve of our OPAMP, which validates the correct functionality. And in the two tables on the right, we present the OPAMP performance under 5 different corners. And we also give a summary of the performance for the metrics, including gain, GBW, PM, IDC, and SR. We present the worst performance under the 5 corners. And for the other 3 metrics, we present the results under the TT corner. Our design hits the highest GBW, SR, and the highest CMRR, which shows its excellent performance. In conclusion, in this work, we present an LLM-based approach that uses multiple agents to automate the parameter tuning process of OPAMPs. It is fast, which takes only about 2 minutes. It is also efficient and interpretable, which gives us a transparent design process. And our future works plans to design an end-to-end OPAMP design framework that also includes the topology selection and the layout phase. We also plan to achieve autonomous task decomposition in the multi-agent design system. And that's all the presentation. Thank you.
Okay, thank you for your impressive presentation and congratulations. Now we have the last presenter, who led the 3rd place of track team.
Okay. So good afternoon, everyone. So good afternoon, everyone. I am Yihan Gu from School of Microelectronics, Fudan University. Today, on behalf of my team, I am thrilled to present our work, Automated Analog Circuit Design using a multi-agent LLM framework. My presentation will be divided into 5 parts shown below. Firstly, I will make a brief introduction. Problem formulation comes after that. Proposed framework along with experimental results is going to be talked about then. And last, I will draw a conclusion. So let's dive into our work now. Analog circuits, such as operational amplifiers, are the unsung heroes of modern electronics. They enable critical functions in medical devices, communication systems, and more. However, their design remains notoriously complex. Even for a simple operation amplifier, weeks are spent on iterating between topology adjustments and parameter tuning to meet specifications like gain, bandwidth, and power efficiency. While existing automation tools such as Bayesian optimization or reinforcement learning
offer partial solutions. They face two critical limitations. First, they focus narrowly on either parameter tuning or topology search, ignoring their interdependence. Second, these methods act as black boxes, lacking interpretability and failing to integrate domain-specific knowledge. Here's where large language models enter the picture. LLMs have revolutionized digital design by generating RTL code from natural language. However, applying them to analog design poses unique challenges. One is known as a semantic gap. Translating high-level specifications into precise SPICE netlists is tricky. Another challenge is data scarcity. Expert-level analog design data is proprietary and scarce. To overcome this, we propose a multi-agent framework that synergizes LLMs with domain expertise. Rather than treating LLMs as standalone tools, we embed them into a collaborative system of specialized agents, designing, simulating, and refining circuits iteratively. Formally, operational amplifier design is a constrained multi-objective optimization problem. As shown here, we maximize a weighted sum of normalized metrics, DC gain bandwidth reduct, aka GBW, phase margin, aka PM, slew rate, aka SR, and power efficiency, while strictly satisfying 5 hard constraints from the AICAS 2025 Grand Challenge. So these are the constraints include the specific values that we are all familiar with, so I just go past it. Notably, optimizing both topology and parameters creates a combinatorial explosion, demanding a novel approach. Okay, here comes to the architectural overview. We propose an automated system with 3 specialized agents in an iterative loop. As you can see from the diagrammatic drawing that the 3 agents collaborate in a closed loop. The design agent generates SPICE netlists using LLMs. The simulation agent validates design via SPICE analysis. The analysis agent diagnoses bottlenecks and suggests improvements. This loop continues until a design meets all specifications, efficiently balancing exploration and exploitation. And our framework rests on 3 pillars: conditional co-design, iterate until all constraints are met; stochastic exploration, leverage LLM diversity via temperature scaling to create various candidate designs; and the self-regulated workflow. A central controller manages the process using state machine logic, ensures robustness and traceability. So let's unpack each agent's role. The design agent uses Quen 2.5-7b LLM to generate SPICE component netlists. It enforces the design rules like transistor width 0.2 to 100 micrometers via constrained beam search. In terms of the simulation agent, it executes AC, transient, and the DC SPICE simulations, as well as extracts metrics like gain, PM, SR, and flex errors like convergence failures. And the analysis agent translates numerical results into actionable advice. For example, increase M1's width to boost GBW. It also validates suggestions against PTK rules to ensure physical feasibility. Our workflow operates in batches for efficiency. Parallel design generation. The design agents proposes 100 plus candidates with controlled randomness. Each of them is simulated in isolation. Composite scoring. Each candidate is evaluated on constraint satisfaction with the outcome only pass or fail, and the normalized performance metrics, which is marked as a relative quality. And the adaptive selection, based on definition, the top candidate advances while the others are discarded. This approach balances exploration that discovers new topologies with exploitation that refines high potential designs, accelerating convergence to optimal solutions. We tested our framework using the open source Skywater Sky 130 PDK and the Qwen 2.5-7b LLM. And our goal is to autonomously synthesize an operational amplifier meeting the AICAS 2025 specs. And our results. Our framework delivered gain 71.00 dB, exceeding the 60 dB threshold. GBW 35.57 megahertz, surpassing 20 megahertz. Phase margin 62.94 degrees above the 60-degree requirement. Slew rate 20.24 volts per microsecond over 20 volts per microsecond. Static current 454.54 microampere under the 500 microampere limit. Moreover, as to additional metrics like CMR, PSR, and input noise shown here, further demonstrate robustness. Remarkably, these results rank our framework among the top 3 in the AICAS 2025 competition in this track. In summary, there are several key takeaways that can be reviewed from our works. First one is effectiveness. All critical specs are met or exceeded. The second one is efficiency. Design cycles are reduced from weeks to hours. Third one is interpretability. Human readable suggestions bridge the black box gap. And in conclusion, we've demonstrated that LLMs, when embedded in a structured multi-agent framework, can automate an analog circuit design without sacrificing performance or interpretability. This work opens doors to broader applications from PLLs to data converters and underscores LLM's transformative potential in EDA. Alas, as an undergraduate student new to analog circuit design and AI-driven automation, I deeply appreciate your patience and the chance given to me. Please forgive any limitations in my understanding of LLM-based design methodologies. Thank you. Merci beaucoup.
Okay, congratulations. Okay, the most exciting moment we have been waiting for is the award ceremony. Now let's.
So what was the order of the presentation? I can post it. Okay, so
Where are the prices?
oh, yeah, it's over there. So so maybe I will end off with the award ceremony. So my name is Xiaopu. So it's a great honor that we have Professor Andre, our VP conference, and Professor Silva, our general chair, to present the awards to the winners over here. So Professor Maui will set up the stage. Then Maui, you want to announce the winners? Okay.
Oh, we already checked the front.
Okay, but what's the order of the winners?
Third.
Oh, you have to
Third,
need to
second,
read.
first.
Yeah, you have to read.
We start with the third.
Yeah.
No?
Yeah.
Yeah, we have 3 checks. For check 1, the third place is Long Haochen, Yina Zhao, Shi Wang, Gao Yuanzhang, and Hui Yuanzhang. Please come to receive your certificate.
Congratulations, come up here. So this is you are 5 here.
For the
What
first
are
one,
the other 3?
He's the first one. He's the first one, Long Hao.
The first, he's an undergrad year 3 student.
Congratulations, great rating.
Congratulations. Anybody taking pictures?
Yeah, they're the photographers.
No pictures?
Yeah, it's right in front, sir. Just, yeah.
Pictures. Come. Okay, sure. What are you, okay, so you say that a great challenge.
And for this trick, the second team is team members are 卢超帆、文苑赵、赵仓、香叶 and 余杭。
Congratulations. Ah, très bien, très bien. Vous parlez le français? No, just
And for optimization check, top one team members are 赵德王、晋尧、监好张。
Congratulations. Congratulations. Now put this right here. Okay, now we take the picture.
And for second trick, this trick is LM hardware system design. The third team members are 玉洁马、林奇李、玉曼珍 and 支瑞房。另外两只是先上是吧？对。那个这个三的话都来了，啊，
Congratulations.
第二名没有，第一名。
Your certificate.
The certification yours.
Okay. The other two teams didn't come, so we skip them and to track 3. This track we also have 3 teams. The third team is from Flame University. The team members are Ben Chaozhu, Yi Henggu, and Xiang Tao.
Conversation. So we have to get up on something to beat up. Closer?
Okay. The last team is also from Fudan University. 姬一神、姬章 and 子浩辰。那我们是站前面还是后边？
真的是全部挤过来就挤到很前方，因为它高度太高。
他说那个沟壑。
对对，全部挤上去。
Okay. Practice, and the lesson.
You can take a group photo.
Take a
group photo with the participants. Yeah.
And
So the
all students, please come and we take a photo together.
Yeah, everyone, please come to the stage to take the last photo.
对，可以在这边做。
给你拍照。上去，什么鬼？go。可以站前面的两排。The student can come to the front and take a top spot here. Top spot here for some of the students. 可能站最前面办公一下也可以。好，不这个靠近前面一点，在前面一点半蹲一下，这样的话就不会那么怪怪。来。
对呀，所有人都要去吗？
不是一起拍，哎，绕完就走，就慢慢走。Wait, go. Okay. This is a smart one. I can breathe in there. 我感觉我站在下面。过去。Spread yourself out. Okay. 不用站，后面没有人，不用站，你要站的是后面有人。哦，不用，拍。哦，为什么不找？为什么找那个？我找那个应该进来拍。Thank you. Okay, good.
Pas avant 8 heures, parce que 8 heures, c'est où? Il y a un apéro, et on commence à manger à 9 heures. Donc, à 8 heures, c'est ouvert, ça a ouvert, mais on mange à 9 heures. À 8 heures, il y a un verre avec certaines bières. Non, mais, voilà, mais ça sert à rien de venir.